Another way that alcohols can be synthesized is by reducing any carbonyl compound. So if I have something with a C double bond O, that's any carbonyl compound, if I reduce it, what we end up doing is adding a couple of hydrogens. So we add an H to the C, add an H to the O, and then the double bond becomes a single bond. So any reducing agent, sometimes we put H in brackets in place of any reducing agent. That will turn any carbonyl compound essentially into an alcohol. So just looking at how reductions happen, if I have an aldehyde, so RC double bond O with an H already attached to the carbonyl, the reduction that happens adds on to that, right? And because we only had one R group in the first place, it's primary alcohol. Whereas if I have a ketone, which already has two R groups on it, I reduce that, we end up with a secondary alcohol because we have those two R groups. We have, though, added an H to the carbon, an H to the OH. The key reagent we use for reduction is sodium borohydride, so NaBH4. So that's a very gentle, very safe reducing agent. It makes alcohols out of aldehydes or ketones. So the borohydride ion, it's BH4 minus, B, it's tetrahedral, right? So boron has a negative formal charge to it, but hydrogen is more electronegative than boron. So the hydrogen is what actually has the bulk of the negative charge in BH4 minus. Okay? So that's really the best way to draw it, with 4 partial minus charges on those H's that add up to the 1 minus charge. But borohydride is essentially just a source of H minus, the hydride ion. Hydride is a hydrogen with 2 electrons and a minus charge. So borohydride reduction, it happens in 2 steps. So first is the addition of sodium borohydride in some appropriate solvent like ethanol. Don't really need to worry too much about that on paper anyway. So we add the reducing agent. That gives us a alkoxide intermediate, which we'll see in a second, which needs to be protonated. So second step is just work up with aqueous acid. So any H3O plus will give us an alcohol. So here's our aldehyde. Okay. Reducing with borohydride gives us a primary alcohol. Here's a ketone. Reducing with borohydride gives us a secondary alcohol. Okay. Works great. Look at these fantastic yields. So the reduction with borohydride is just one of the simplest, most reliable reactions that there is in organic chemistry, I would say. The mechanism of borohydride reduction is very, very simple. As long as you remember hydride is an H minus, that's our source of electrons. Carbonyl compounds have a partial plus on the carbon and partial minus on the oxygen. So an H minus will naturally attack the carbonyl carbon, which will kick one pair of those double bond electrons up onto the oxygen. So we've added our H to the carbon. Okay? Our intermediate then is an alkoxide. It has that O minus. If I have any kind of aqueous acid that we add to that, let's get in the habit of drawing hydronium out, H3O plus, because then I can take one of these lone pairs, attack an H of hydronium, put the other electrons back on oxygen, and we get our alcohol. So it's very important you know where each of those 2 hydrogens come from in this alcohol that we've added, right? Because they come from different places. This is from the reducing agent. That's the H on the carbon, because that was the nucleophilic H, right? H minus that added to the carbon. The other one, the OH hydrogen, is just from hydronium, from the aqueous acid that we've added. Okay, so an interesting experiment, whatever happens, whatever you do with hydrogen, you can also do with deuterium, but it's different fundamentally. It's more massive, and it doesn't show up on NMR and so on. So I could add a deuterium to the carbon by using a deuterium-containing reducing agent like NaBd4 instead of BH4. That would put the D in the carbon. If I used regular borohydride, I'd put an H there, but then if I had an acidic deuterium source, okay, like D3O plus, I would be able to make OD. If that, put the deuterium on the alcohol instead. So those hydrogens are added sequentially. It's important you know where each comes from. All right, just like we said, the alkoxide intermediate is neutralized, or like we call it in lab, acidic workup. So after your reaction is done, when you add acid in your separatory funnel or whatever, that makes our alcohol product that we're interested in. So borohydride works on aldehydes and ketones. Okay? If I have something with more oxygens in it, like a carboxylic acid, right, a C double bond OH, okay, or an ester, C double bond OR. We can reduce those down to alcohols, but we need a stronger reducing agent. We need lithium aluminum hydride. Okay, that's Li plus with the aluminum hydride ion, AlH4 minus. Looks just like borohydride, except now the H's are even more partially negative because aluminum is even less electronegative than boron is. So if we count the hydrogens, we need 2 hydrides to be added to the carbonyl to make an alcohol, right? We essentially only have 1 R group here, but no H's. So to get this primary alcohol, like we're making in both cases, whether I have an carboxylic acid or an ester, I need 2 hydride ions to be added. Let's just make sure we get that R, C double bond O, OH becomes R, C, OH with now 2 new hydrogens added. Okay, exact same thing with esters. So we need a more powerful reducing agent in order to add both of those hydrogens. And when we get to the chapters on carboxylic acids and esters, we'll go in much more detail about the mechanism of that. So just know that you need the more powerful aluminum reducing agent, right? Lithium aluminum hydride. If you want to call that LAH, you can. Right? We have Li plus, AlH4 minus. It's Li, AlH4, or LAH. If you write LAH, if you write step 1 LAH, step 2 H3O+, that's perfect. Okay? But that's only needed with carboxylic acids and esters, where we already have another O on the carbonyl carbon. Okay? When I have just an H on the carbonyl carbon, that's an aldehyde. When I have 2 R groups in the carbonyl, that's a ketone. Okay? The gentle sodium borohydride is best to use for those. LAH can be used for all of them, in fact, but we only really use LAH when we have to because it's so reactive. It's actually a little bit dangerous to use.